In sections 7.5 and 7.6, we're going to talk about quantum mechanics and the atom and the shapes of orbitals, which are regions of probability where the electrons can be found. Now remember from the previous video, light energy and electrons share wave and particle-like characteristics. Okay, they're similar characteristics. We talked about characteristics of waves. We talked about light behaving like a particle, a photon. Okay, we know electrons are subatomic particles. They have these similar characteristics. But why do we care so much about the electrons? The electrons, which are located outside the atom's nucleus, are the reason why we have chemical reactions or chemical changes occurring. Okay, you have bonds break and bonds form, and bonds are made of the electrons. So in this video, we're going to talk about the organization of electrons in an atom, and how those electrons are organized. Electrons move around the nucleus in orbital regions, and the orbitals are regions where the electron probably is. We can't determine the exact trajectory of an electron. We can't say this is the orbit that it's in, or trajectory, but we can say it's in this region of probability, which is what is called an orbital. The orbital theory is what distinguishes quantum mechanics from the Bohr model, which specifically talks about the electrons encircling the nucleus in trajectories or orbits. So quantum mechanics, that's one big difference with quantum mechanics versus prior models. Okay? The electrons have quantized energy, specific definite amounts. These electrons containing the energy can jump from one level to another. So they want to be in the most stable ground state, low energy, but they can go to an excited state of higher energy. Okay. The electrons that are outside the nucleus have organization, and the electrons are arranged in energy levels. The larger the atom, the more organization it needs. In the next two boards here, I'm going to go through how the electrons are arranged. Okay, just like a kitchen has a lot of stuff in it. You have food, you have utensils, you have plates, you have cups. So you have a lot of cabinets, you have a lot of shelves. To make all of those contents to have organization to them. Well, the larger an atom gets with increasing amount of electrons, the more organization it needs. So it follows this structure. Okay, you have initially principal energy levels, which are designated by the letter n, the principal quantum number designated by n. And n determines the overall size and energy of the orbital. N is always a whole number greater than or equal to 1. Okay. Within the principal energy levels, you have sublevels. Okay, depending upon the size of the atom and its electrons would depend upon how many sublevels you would need. And the sublevels are represented by the secondary quantum number, which is a letter L, like an italicized L. Some traditional names for the secondary quantum number, it's also called the azimuthal number or the angular momentum number. Okay, all of those terms refer to sublevel designation, the secondary quantum number. L is designated, the sublevels, by SPD or F designation. So we have an S sublevel, a P sublevel, D sublevel, an F sublevel to organize these electrons that are part of the atom. Okay? Now, you've probably heard these letters, S, P, D, F, and you wonder where did they come from. So here's some trivia for you. The letters S, P, D, F stand for sharp, principal, diffuse, and fundamental. And they're named after the types of spectral lines that were generated by these orbitals when analyses were done. So if you ever wonder where the terms S, P, D, F come from, all right, and what they stand for, there you go. Within the sublevels, we have the orbitals. And the orbitals are designated with the quantum number m sub L. The orbitals are spaces for electrons. They're regions of probability of where the electrons could be. They give the magnetic quantum number m sub L gives the orientation of the orbital. Okay, is it oriented along XYZ axes? Is it oriented along the x-axis, the y-axis, the z-axis? It's represented by the magnetic quantum number m sub L. Now, depending upon the type of orbital that we have, and we're going to look at the orbitals in a little bit more detail coming up, M sub L can either be 1, 3, 5, or 7. We have only one type of S orbital. We have 3 types of p orbitals. We have 5 types of d orbitals, and we have 7 types of f orbitals. There's a chart, there's some figures in your book that give these visuals, but I'm going to show you what I have here. Okay, we have only one type of s orbital, it's a sphere. We have 3 types of p orbitals, and they are lobes that are oriented along the x, y, or z axes. The d orbitals, there are 5 types. Okay, and they're lobes that are a little bit more complex than the p orbitals that are located again along either the x, y, or z axes or combinations of those axes. And then the f orbitals, okay, looks like you have a bunch of balloons. You have 7 types of f orbitals, okay, that are lobes oriented along x, y, and z axes, okay, but they're much more complex in shape. So the magnetic quantum number, okay, comes from the number of types of orbitals that you have of that designation. Okay. And then last but not least, you have the electrons, which go into the orbitals. When the electrons go into the orbitals, they have a direction, they have a spin. And that's represented by the magnetic spin number, m sub s. M sub s is either positive half or negative half, depending upon the electron spin. If the electron is in that orbital and has an upward spin, it has a positive 1/2. If the electron in that orbital has a downward spin, negative 1/2. Okay. So that's the overall organization of how the electrons are organized in an atom. Okay, now we can't see electrons with our eyes, but we can envision them, okay? We can envision them. We can use scanning electron microscopes to see atoms. So we're going a deeper level into that atom and what constitutes that atom. And the electrons are one of the particles that are a very important part of the atom. In the next couple screens here on the board, I'm going to go into a little bit more detail about the principal quantum number and the principal energy levels, the sublevels, the orbitals, and the number of electrons. And ultimately, having this understanding will allow us to go into topics in Chapter 8, such as electron configurations. We're going to look at the periodic table and look at the number of electrons that an element has and be able to write the organization of that atom's electrons. Okay, but we need to have this understanding first of how everything is organized before we can actually organize it. Okay? Let's look at those energy levels and sublevels in a little bit more detail. Okay? The first designation is the principal energy levels represented by the principal quantum number n. When n equals 1, the electron is in its ground state, lowest energy. When n goes up, 2, 3, 4, 5, so on, all the way up to 7, the electron is in an excited state of higher energy. Okay. The larger the atom gets, the more principal energy levels you have, because you have more electrons to organize. Likewise, the more electrons that you have to organize requires more sublevels. So the sublevels, okay, with the designated by the secondary quantum number or the azimuthal number, okay, principal energy levels are divided into sublevels. The sublevel S is the lowest in energy and the sublevel F is the highest in energy. Now when you have a small atom, okay, and n equals 1, you have only one sublevel, okay, the 1s sublevel. It's a small atom. You do not, and it only applies to a few elements, okay, where you only need that first principal energy level and the first sublevel. As the atom gets bigger and you have more principal energy levels, you introduce a second sublevel, the p sublevel. Okay, you don't have a p sublevel in the first principal energy level because the first principal energy level is too small. So the atom's getting larger, okay? You have higher energy, you introduce a second sublevel, 2p. The atom gets larger. You need more space to accommodate these electrons. When n equals 3, you have the introduction of the third type of sublevel, the D sublevel. So the D sublevel comes in the third principal energy level. You will not see 2D because the 2D, because the second principal energy level is too small to have a third sublevel. So the first sublevel, okay, the first principal energy level, you only have the S sublevel. The second principal energy level, you have the introduction of the P sublevel in addition to the S. In the third principal energy level, you have the introduction of the D sublevel in addition to the S and the P. And then when the atom is so large that you introduce the fourth principal energy level, you also introduce a fourth sublevel, the F sublevel, to accommodate the amount of increasing electrons. Okay? In the fourth principal energy level, you can have an S sublevel, a P sublevel, a D, and an F. Okay? So the less than signs are showing you that, yes, the S sublevels, regardless of which principal energy level they are in, are lower in energy than P. Any P sublevel, okay, within that principal energy level is lower than a D, and a D sublevel is lower than an F sublevel. The orbitals are where the electrons are actually located, but we cannot pinpoint the tiny electron's exact location. Remember, the electron is moving, okay? So we have orbitals, and they have different shapes, and I was showing you a little bit earlier these pictures here, okay, which represent the shapes of the orbitals. So we're going to talk a little bit more in detail now about these. But note in your textbook, figures 724 through 729 give you representations of what I'm showing you here with this illustration, okay? This illustration just has everything on one page, but you have the same pictures in your textbook with these figures. Okay, the s orbital is the most simplistic. You only have one type, and it's a sphere, okay? And you have that sphere that goes through the three axes, x, y, z axes. And the s orbital is represented by the azimuthal number of L equals 0, okay? The magnetic quantum number for the s orbital is represented by m sub L equaling 0, okay? Only one magnetic quantum number for the one type of s orbital. The p orbitals, we have three types. We have lobes that are oriented either along the x, y, or z axes, okay? X, y, or z axes, you have a set of lobes, okay? And the electrons could be in any location within those lobes that are the p orbitals. You have three types of p orbitals, okay? The p orbitals are represented by the secondary quantum number or the azimuthal number L equals 1, okay? The magnetic quantum number, you have three possibilities because you have three types of p orbitals. And the three possible magnetic quantum numbers for m sub L are either -1, 0, or +1. Three magnetic quantum numbers representing the three types of p orbitals that you could have. The d orbitals, we have five types. Five types of d orbitals, and they're a little bit more set of they're more complex lobes oriented along the x, y, and z axes. Okay, usually they're oriented along two of the axes, either x, y, or y, z, or x, z, or so they're more together. Okay, so we have five types of d orbitals. Azimuthal number L equals 2. That's a secondary quantum number. And we have five possible magnetic quantum numbers for the five possible types of d orbitals. The magnetic quantum numbers, m sub L, represented by -2, -1, 0, +1, or +2. Okay, five possible numbers for the five types of d orbitals. The f orbitals, okay, which are very complex, and they actually only apply to the lanthanides and actinides of the elements, okay, are very complex. It looks like you have a bunch of balloons there for a birthday party, okay, when you look at the f orbitals. Okay, you have a complex lobes along the x, y, and z axes, and you have 7 possible shapes for the f orbitals. So the azimuthal number, secondary quantum number, L equals 3. The magnetic quantum number, you have 7 possible magnetic quantum numbers for the f orbitals because you have 7 types of f orbitals. And those 7 magnetic quantum numbers for the f orbitals are -3, -2, -1, 0, +1, +2, and +3. The number of electrons that go into a single orbital is governed by the Pauli exclusion principle. The Pauli exclusion principle states that at most 2 electrons can occupy a single orbital. Regardless of how complex that orbital is, at most only 2 electrons can occupy it. You can have a simple s orbital here, or you can have a complex f orbital over here, and at most only 2 electrons can fit into any of these. At most 2, at most 2, at most 2 in each, and at most 2 in each, regardless of its shape, okay, or complexity. When an orbital has no electrons in it, we say it's an unoccupied orbital. When an orbital has 1 or 2 electrons in it, we say that it's an occupied orbital. When you have electrons that are paired within an orbital, you say that those electrons are diamagnetic. Okay, one is spinning up and one is spinning down. Okay, they have opposite magnetic spin numbers. Okay. When you have paramagnetic electrons, they are unpaired and single, and they're spinning upwards with a magnetic spin number of m sub s number of a +1/2. Okay, so these are some terms that are used to describe the electrons and the orbitals. Remember, from all of these concepts in this video, electrons go into the orbitals. The orbitals are in sublevels, and the sublevels are in principal energy levels. Okay, when we approached this at the beginning of this video, we started with the broader category of the principal energy levels and worked down to the little teeny electrons. But if we work up, electrons go into the orbitals, orbitals are in the sublevels, and the sublevels are in the principal energy levels. You can use any kind of analogy. You can use an analogy of books in a bookcase. Okay, you have books that contain pages. The pages are in the books. The books go on the shelves. The shelves are in the bookcase. Okay, any kind of a hierarchy. I was talking about a kitchen earlier. Okay, you have your utensils. You have your forks and knives and spoons. You usually have them in a container that organizes them: forks, knives, spoons. Okay, then they go into a drawer, and the drawer is part of a cabinet or a section. Okay, and then that is part of the kitchen. Right, so any kind of a compartmentalizing analogy you want to use. Okay, but each sublevel, therefore, because it only contains so many orbitals, and the orbitals can only contain at most 2 electrons, each sublevel has a maximum amount of possible electrons. That information we're going to be able to use to help us to write electron configurations, which are the arrangement of electrons in an atom. So we're going to take all of these concepts, or most of these concepts from this video, okay, and we're going to use them for the sections in Chapter 8 that we're going to start off with, right? So we're going to now learn about the maximum amount of electrons in a sublevel. Let's look at that. The maximum number of electrons per sublevel is equal to the product of the number of types of orbitals times 2. Okay, since at most 2 electrons can be in an individual orbital. Okay, an s sublevel with an s orbital and only one type of s orbital we have can fit at most 2 electrons. So the maximum number of electrons per an s sublevel is 2. A p sublevel containing p orbitals, 3 p orbitals, can have at most 6 electrons. Okay, it can have fewer, but it can have no more than 6. A D sublevel, okay, when we say a D sublevel, it can be 3D, it can be 4D. Okay, it can't be 2D, because remember, the D sublevel doesn't start until the 3rd principal energy level. When it comes to a D sublevel and D orbitals, we have 5 types of D orbitals. 5 orbitals at most, each fitting 2 electrons, gives us a total of 10 electrons per sublevel, at most, at maximum. And then an F sublevel with F orbitals, 7 possible F orbitals can have at most 14 electrons per F sublevel. Okay, and we have 4F. The F sublevel doesn't come up until the 4th principal energy level. Okay, and so we can have at most 14 electrons in an F sublevel. You can have fewer, but you can have no more than 14. So we're going to take this information, and the next video, which will be focusing on chapter 8, okay, we're going to go into using this information to writing electron configurations.